Welcome to a 3x3 example of variation of parameters. So recall, if we have the system y prime is equal to a of t, y prime is equal to a of t times y plus f of t, a of t an n by n matrix, f of t a vector. And if y1 through yn form a fundamental set of solutions, for the homogeneous system, y prime equals a of t times y. Then the non-homogeneous system has solution y equals capital Y of t times u of t, where capital Y of t is the fundamental matrix, first column y1, last column yn, and u satisfies capital Y of t times u prime is equal to f of t. So we're going to go ahead and do a 3x3 example. Let's find the general solution to y prime equals the 3x3 matrix A times y plus f of t, where A is 1, 2, 1 for the first row, 0, 1, 1 for the second row, and 0, -1, 3 for the last row. And f of t is 0, then 2e to the negative t, and then 0. So just a quick note, y1 equaling 1, 0, 0 times e to the t, y2 equaling 3, 1, 1 times e to the 2t, and y3 equaling 3t minus 2, t plus 1 times e to the 2t form a fundamental set of solutions to the complementary homogeneous system. So to then find our non-homogeneous general solution, we're already partway there. So we need to find the non-homogeneous solution, or non-homogeneous general solution. So we have y of t, capital Y of t, would be y1 in the first column, which is just e to the t, 0, 0 for our first column. Then we have y2 for our second column, so that should be 3e to the 2t, and e to the 2t, and e to the 2t for our second column. y3 in our third column, so that would be 3t minus 2 times e to the 2t, then t e to the 2t, and last up t plus 1 times e to the 2t. So this is our capital Y of t. So we are looking for u. such that y of t times u prime is equal to our f of t. So we are looking at e to the t, 0, 0 for our first column, then 3e to the 2t, e to the 2t, e to the 2t for our second column, 3t minus 2, e to the 2t, t e to the 2t, and t plus 1 times e to the 2t. All multiplying u prime should be equal to, our f of t was 0, 2e to the negative t, 0. My screen. Right, we can solve this however we like. This actually lends itself fairly nicely towards row reduction if you want to do row reduction. So we are looking at the augmented matrix, e to the t, 3e to the 2t, 3t minus 2, e to the 2t, with augmentation 0 for our first row. Then we have 0, e to the 2t, t e to the 2t, and 2e to the negative t for our augmentation for our second row. And last up we have 0, then e to the 2t, and t plus 1 e to the 2t, augmentation 0 for our last row. If we do row 1 times e to the negative t, then we have 1, 3e to the t, and 3t minus 2 times e to the t, with augmentation 0. If we do e to the negative 2t times row 2, and e to the negative 2t times row 3, we have 0, 1, t, and then 2e to the negative 3t for our second row. For our last row, we would have 0, 1, t plus 1, and then 0. If we now do leave row 1 alone, leave row 2 alone, and then if we do row 3 minus row 2 for the last row, we would have 1, 3e to the t, 3t minus 2 times e to the t, with augmentation 0 for our first row. We would have 0, 1, t, and 2e to the negative 3t for our second row. Our last row becomes 0, then 1 minus 1 is 0. T plus 1 minus t is 1, and 0 minus 2e to the negative 3t is just negative 2e to the negative 3t. If we wanted to keep going, we can, absolutely. If we do leave row 3 alone now, and if we do row 2 minus t times row 3, we would have our third row is 0, 0, 1 with negative 2e to the negative 3t. Our second row is 0, 1, 0. And then we would have 2e to the negative 3t minus 2t, minus negative 2t e to the negative 3t. So that becomes 2 times t plus 1 e to the negative 3t. And then if for our first row, we do row 1 minus, sorry, I need more room. We do row 1 minus 3t minus 2 e to the t times row 3. We would have 1, 3 e to the t, and then 0 for the last position before the augmentation. I apologize, I need to update my screen. So again, when we did our row 2 minus t row 3, that served to give us just 0, 1, 0 for the left-hand side second row. The augmentation became 2 times in parentheses t plus 1 times e to the negative 3t. Now we are eliminating the third column in our first row by doing row 1 minus 3t minus 2 times e to the t times r3. So that gives us 1, 3 e to the t, 0 for the left-hand side. The right-hand side, we are subtracting off 3t minus 2 times e to the t times negative 2 e to the negative 3t. So that becomes plus 2 times in parentheses 3t minus 2. And then e to the t times e to the negative 3t is e to the negative 2t. If we want to get down to just the identity on the left-hand side, if we again leave row 2 and row 3 alone, and do now row 1 minus 3e to the t times row 2. Our last 2 rows stay the same, so row 2 will still be 0, 1, 0. And 2 times in parentheses t plus 1 times e to the negative 3t. Our third row will still be 0, 0, 1, and then negative 2 e to the negative 3t. Our first row will have 1, 0, 0, and then we'll be subtracting off 3 times negative 2 e, sorry, we'll be subtracting off 3 e to the t times 2t plus 1 times e to the negative 3t. So that becomes, we have our 2 times 3t minus 2 e to the negative 2t. Then we are subtracting off 6 times t plus 1 times e to the negative 2t. Oh, I just realized I have some scratchbook. I'm going to erase that quickly. All right, at this point, we just have 1, 0, 0, and then we'd have 6t minus 6t will cancel out. We have a negative 4 minus 6 becomes negative 10. So we have negative 10 e to the negative 2t for the augmentation position in the first row. Then we have 0, 1, 0. And then we have 2 times in parentheses t plus 1 times e to the negative 3t. And 0, 0, 1, and then augmentation negative 2 e to the negative 3t. So if you go all the way down to the identity matrix on the left, the right-hand side is our u prime. So we have u prime is equal to negative 10 e to the negative 2t for the first position, 2 times t plus 1 times e to the negative 3t for a second position, and negative 2 e to the negative 3t for a third position. If we go ahead and integrate, we're just integrating u prime with respect to t. So the first position isn't not too bad. We should just get 5e to the negative 2t. The third position is not too bad. We have 2/3 e to the negative 3t. And then to do the integral for 2t plus 1. Let's do 2 times t plus 1 is our u. And dv, we will do the e to the negative 3t. So differentiating down the u, we go to 2 and then we go to 0. Integrating the dv, we would have negative 1/3 e to the negative 3t, and then positive 1/9 e to the negative 3t. We do the positive product on the first diagonal, negative product on the second. So we are getting negative 2/3 times t plus 1 times e to the negative 3t, and then also a minus 2/9 e to the negative 3t. And then I'm going to actually write in the plus C1, C2, and C3 as well, since we are integrating. So that first row will have a plus C1, second row will have a plus C2, last row we have a plus C3. Simplifying our u just a little bit, we have 5e to the negative 2t plus C1. Then we have negative 2/3 t. Minus 2/3 minus 2/9 is minus 8/9. All times e to the negative 3t, then plus C2. And then we have 2/3 e to the negative 3t plus C3. At this point, our final solution, we go to find the solution. We simply have that y is equal to our matrix y of capital Y of t times our u of t. Or we could do u1 times vector 1 plus u2 times vector 2 plus u3 times vector 3. And then, so this is u1 times y1 plus u2 of t times y2 plus u3 of t times y3. So u1, we had 5e to the negative 2t plus c1. Multiplying y1 was 1, 0, 0 times e to the t. Then we have, actually, I'm going to move this down to the next spot. There we go. Then we have plus our u2 was negative 2/3 t minus 8/9 times e to the negative 3t plus c2. So we have negative 2/3 t minus 8/9 all times e to the negative 3t and then plus c2. All of that is multiplying 3, 1, 1 times e to the 2t. And then for our last position, our u3 was 2/3 e to the negative 3t plus c3. So we have 2/3 e to the negative 3t plus c3. And this is multiplying. We had 3t minus 2. Let me remind, yes, 3t minus 2. And then t, 2t, and t plus 1. Let me, sorry about this. That's a long scrolling. Sorry, just t. So 3t minus 2t and t plus 1. all times e to the 3t. So we can go ahead and rearrange this if we like. This becomes 5 times 100, or other words known as 500. And then we have e to the negative 2t times e to the t is e to the negative t. Then we have, I'm going to do our plus C1, C2, C3 at the end. Then we have plus, we would have negative 2/3 t minus 8/9 times 3 times 1 and times 1. And then e to the negative 3t times e to the 2t is again e to the negative t. So that first position would be negative 2t minus 8/3. Our second position would be a negative 2/3 t minus 8/9. And our last position again would be a negative 2/3 t minus 8/9. This is all multiplying again, e to the negative t. Then once more, we have 2/3 times 3t minus 2 would be 2t minus 4/3. Then we have a 2/3 times t, and 2/3 times t plus 1, or 2/3 t plus 2/3. Once again, this is e. I apologize. This should have been a times e to the 2t when I did our u3 times y3. So again, we get a times e to the negative t. And then we have our homogeneous general plus C1 times 100 times e to the t plus C2 times 311 times e to the 2t plus C3 times 3t minus 2t and t plus 1 times e to the 2t. We can, of course, simplify that first part. We have a negative 2t plus 2t cancels out. We have a negative 4/3 minus 8/3 is negative 12/3, otherwise known as negative 4. And 5 minus 4 is just 1. So we'll have a 1 in our first position. Then we have a negative 2/3 t plus 2/3 t cancels out, and just negative 8/9 in our second position. And then we have a negative 2/3 t and a positive 2/3 t cancels out. And a negative 8/9 plus 2/3 would be a negative 2/9. All of this times e to the negative t. Then we have our plus C1 times 100 e to the t plus C2 times 311 e to the 2t plus C3 times 3t minus 2t t plus 1 times e to the 2t. So this is our final general solution. Using variation of parameters on the 3 by 3 case.